Welcome to our explainer. We're about to tackle a really wild idea. What if the most important numbers in our universe, like the speed of light, aren't just random? What if they're actually built into the very fabric of geometry itself? Right. Let's just jump straight into one of the biggest questions in all of physics. You've got these fundamental constants of nature, right? These numbers that literally define everything. But where did they come from? Why do they have the exact values they do? I mean, think about the speed of light, c. In physics class, we're taught it's just this number we measure really, really well, and then we plug it into all our equations. But what if it isn't just some random value? What if it's the only speed it could possibly be? And it's not just the speed of light. This puzzle gets even weirder with something called the fine structure constant. This number, about 137, rules over all of electromagnetism. And honestly, its origin is one of the deepest mysteries we've got. So, how do you even begin to answer this? Well, there's a speculative idea out there, a framework, that gives a pretty radical answer. It says these constants aren't random at all. Instead, they just fall out of a single repeating geometric pattern that builds the entire universe. And that idea is right here in one of its core axioms. The claim is absolutely massive. There are no dials to turn in the cosmos, no what-ifs, just a single geometric structure, and all the constants of nature are baked right in from the start. Okay, so how is this supposed to work? It all starts with something surprisingly simple, a balanced set of three little values. The one in the middle, the zero, spins along a line. This generates the electric field, or E. The other two values, they rotate in flat planes, generating the magnetic field, B. Now here's the kicker. A line and a plane are naturally perpendicular, right? So in this model, the E and B fields have to be perpendicular. It's not a coincidence. It's a geometric necessity. So we've got this geometric structure. How in the world does that get us to the speed of light? Well, according to this idea, c isn't just a speed limit. It's more like a condition for existence. Inside this geometric vortex, there's apparently a perfect point of balance, a state they call rest. Think of it as a geometric sweet spot where everything is in perfect harmony. The electric field strength is exactly the same as the magnetic field strength. And here is the big payoff. The speed of light, c, is supposedly the only velocity that makes this perfect E equals B balance possible. This is their explanation for why a photon can travel forever without running out of steam. It's not just moving fast, its speed is what's holding it together in perfect balance. And this E equals B balance isn't just some abstract concept. It has real-world consequences. This perfect geometric state is what supposedly sets the impedance of free space, that 377 ohm number that's so crucial for all of electronics and electromagnetism. It's presented as a kind of signature of this underlying geometric unity. All right, now for the main event. Let's see how this same idea tries to derive the fine structure constant, a number the legendary physicist Richard Feynman once called one of the greatest damn mysteries of physics. And here it is. This is the centerpiece of the whole claim, a formula for the fine structure constant that's, well, shockingly simple. It's built from nothing but pi, the number of rotation, and its first three powers. That's it. Now, this isn't just a bunch of numbers thrown together. Each piece of the formula is said to represent a real geometric feature of that vortex. The big 4 pi cubed term, that's the volume of the rotating magnetic fields. The pi squared term, that's the surface area where the electric and magnetic fields meet. And that last little pi, that's the contribution from the electric field spinning on its axis. It's like a recipe for building the thing. So what happens when you actually crunch the numbers? You plug pi into this geometric recipe, and you get about 137.0363. The framework calls this the intrinsic value, the pure geometrically perfect version of the constant. And you know what? It is unbelievably close to what we measure in labs. But it's not exactly the same. And this is where things get really interesting, because the framework introduces this incredibly clever twist. I mean, just look at the numbers. They're close, really close, but there's a tiny, undeniable difference between the number from the geometry and the number we get from our best experiments. So what gives? Does that tiny gap mean the formula is wrong? Is this whole thing just a really, really lucky guess that got close but ultimately failed? Well, the framework's answer is a hard no.
In fact, it claims that difference is not only expected, it's predicted. Think about how you see color. Your eyes don't just passively receive light. Your brain actively constructs the idea of red or blue from the signals it gets from 3 different cone cells. What you see is a construction, not a direct reading.
So the argument goes that tiny difference we saw, that's not an error. That's the predictable shadow that gets cast when we, at our huge human scale, try to observe a tiny quantum scale phenomenon. So far from being a flaw, this little discrepancy is actually presented as proof that the theory's model of observation is correct.
Okay, this whole idea of turning a flaw into proof, it really points to a much deeper, more fundamental claim about what math even is in relation to reality.
Let's be really clear about how different this is. In mainstream physics, math is the language we use to describe what's happening. It's a tool. We have Maxwell's equations that tell us E and B are perpendicular, and then in a totally separate math class, we learn that sine and cosine are orthogonal. This framework says, no, those aren't two separate things. It claims the math is the geometry. The reason sine and cosine are orthogonal is because the E and B fields are physically perpendicular.
And that leads us to one last really mind-bending question. If this whole idea is right, if the imaginary number I isn't just a math trick, but actually represents a physical 90-degree turn, and pi represents a physical rotation, then what does that mean for our most beautiful equations? If you take that geometric perspective seriously, then Euler's identity suddenly becomes something more. It's not just an elegant mathematical curiosity anymore. It transforms into a profound statement about physics, a kind of fundamental law describing the geometric conditions required for existence itself.